In this lecture, we continue with where we stopped in the last lecture, that is parallel axis theorem. So in this parallel axis theorem, we say that the moment of inertia about any given axis, right, will be given by the moment of inertia about the common center of mass plus mh squared, where big M is the total mass of the rigid body, h will be the perpendicular distance from the h perpendicular distance from the given axis to the axis that passes through the center of mass. Okay, so we need these two axes to be parallel. That's why parallel axis theorem reminds us that the two axes must be parallel. So if you recall, in the last lecture, we took a look at page 30. So I'll bring you there now. Okay, this is the one, table 2. Page 30. This is the one, table 2. Okay, so in this table here, you have rotational inertia with some common shares axis indicated. So usually it's an axis through the center of mass. So in A, you have the moment inertia for about central axis. Okay, then you also have the annular cylinder. So this one you're expected to know how to find the moment inertia by integrating. The C solid cylinder or disk, they have the same moment inertia. This one you're also expected to know how to derive. Followed by that, in D we have moment inertia for solid axis. For solid cylinder, or this about the central diameter. Okay, this one not expected to derive because we can't just use what we have, the parallel axis theorem. We need another theorem, which is the perpendicular axis theorem. Okay, so this one you just need to recall. Similarly for the others, right, even B and C, if the question didn't ask you to derive, you can just recall. Okay, then this one is what we had done before. This is the thin rod about the axis through the center perpendicular to the length. So because the rod is thin, therefore you can assume that the thickness is negligible. So we do it in one dimension. This is the thin rod is in the example form. Then we have F, which is for sphere. This is also difficult to derive, so not expected for sphere. Another sphere, but this one is a thin spherical shelar about any diameter. Then this is a hollow sphere, not expected to derive. Then you have the hook, followed by the cuboid, which is a slab. So this is the rotational inertia. So you only expected now to derive B, C, and E. The rest, you can just recall. Okay, let's go back to our perpendicular axis theorem. Let's take a look at what example part B. So the part D, what example 4 is actually two particles. The thin rod one is what example 5. That's not stable. Okay, let's take a look at 4B. In this case, you're asked to find the rotational inertia of the body about an axis through the left side of the rod and is parallel to the first axis. Okay, so initially you're given the two particles, right? The axis of rotation pass through the center of the rod, and we have derived it using summation mr squared. Okay, so we can choose to use the parallel axis theorem. That means now the axis will be on the left side, which is here. and therefore the perpendicular distance will be just half of the length of the rod. Okay, total mass of the system is 2m. So using the parallel axis theorem, the moment inertia now about the new axis will be the moment inertia about common center of mass plus mh squared. So the m is 2m, h is half the length of the rod, which is L over 2. So we end up with ml squared. Or since it's conserved two particles, we can actually use the defining equation for rotational inertia again, summation mi ri squared. Okay, so for particle 1, which is the one on the left, it passed through the axis of rotation, so the r is 0. For the second one, the distance from the particle to the axis of rotation is exactly L, so we end up with ml squared. So whether you use parallel axis or you just start from scratch, well, the workings are comparable. Okay, let's take a look at example 5. Here we have the thin rod, so this is the one dimension rigid body. Our mass is m, length is L, and the axis of rotation initially passing through the center of the mass. Now you are asked to find what in part B, what is the rod's rotational inertia about a new rotation axis that is perpendicular to the rod and to the left end, so this side. So we can use the parallel axis theorem. Okay, so we call the moment inertia for the rod, which is 1 over 12 ml squared. So we derive above in part A, then plus the total mass of the system, which is small m, and the distance between the two axes, perpendicular distance between the two axes is half L. So with that, we get 1/3 ml. Or what you can do is, you can integrate, that means you start from scratch again. For rotational inertia, for continuous body, you just integrate r squared with respect to dm. And using the same concept as we have discussed in part A, okay, we assume that the density, linear density is same. So mass over length, right, m over L, will be the same as the mass element dm over dr. So your dm will be ml over dr. So using that same concept, I sub in my dm here. Okay, so this is the same expression as in part A, but the limit, right, now I will have to integrate from 0 to L. So you end up with half, 1/3 ml squared. Okay, let's take a look at work example. Next one. And then this is all for example 7 done. Next one will be work example 8. Okay, here you're given a rigid sculpture, consists of a thin hook here. So this is the thin hook, and the radius is given, the mass is given. Given another rod, the mass is m, same as that of the hook, and the length is 2.0 r. Okay, what r is the radius of the hook, is arranged in the diagram below. So you are told that the sculpture can pivot around a horizontal axis. So this is the horizontal axis, so it will rotate this way now. And this horizontal axis pass through the center of the hook. So in part A, in terms of m and r, what is the sculpture rotational inertia about the rotational axis? Okay, so in this sculpture, it consists of two shapes. One is a hook, the other is a rod. You can find the moment inertia for the hook and then find that of the rod, add them together. That will give you the total rotational inertia. The reason why you can do this is because rotational inertia is a scalar. So if you have many of these rigid bodies come together to give you a composite body, you can just find the individual and sum the rotational inertia together. Okay, so to find the rotational inertia of the sculpture. Firstly, it will be good practice to list out what we have. We have the mass of the hook, radius of the hook, the rod mass, as well as the length. So like what I say, we will separately find the rotational inertias of the hook and the rod, and then add them together. Recall for the hook, the rotational inertia, right, will be half mr squared. Okay, about any diameter. So this rotational axis is about one diameter of the hook. Then for the rod, we will have to use the parallel axis theorem because the axis of rotation is not passing through the center of the rod. Okay, so the rod is uniform. It's not mentioned as uniform, we have to assume it's uniform. So the center of mass of the rod will be in the middle here. So the distance from an axis that passes through the center of the rod to this axis of rotation will be given by L over 2 plus R. Okay, so the distance from here, which is the axis passing through the center of mass of the rod, to the given rotation axis will be L over 2 plus R. So using the parallel axis theorem, the moment inertia of the rod will be the moment inertia from the center of the rod. Okay, so this one we call plus m h squared, where h is given by r plus L over 2. L is 2r, so you end up with L over 2 being r. So simplifying, the total moment inertia is 4.83 mr squared. In part B, starting from rest, the sculpture rotates about the rotational axis from the initial upright position as shown above. What is its angular speed omega about the axis when it is apart? Okay, so we go back to the diagram. So this is the initial position. Then it's going to rotate until it's inverted. So when it's inverted, the hook, okay, will still look the same, but the rod, right, instead of on top, it will be below here. Okay, so this will be the inverted position. You are asked to find the angular speed omega when it is inverted. So at the instant when it is inverted. So we are using a universal concept here, that is conservation of energy. Okay, initially the hook and the rod, which is the sculpture, is not rotating, so omega naught will be 0. So from the law of conservation of energy, the gain in the rotational KE, okay, only rotational, there is no translational motion. So the gain in rotational KE will be equals to the loss in the GPE. Okay, the loss in GPE for the sculpture will have to measure respect to the center of mass of the sculpture. Recall rotational KE is half I omega squared. And the loss in GPE will be mgh, where the total mass of the system, the hook plus the rod, is 2m times g, and the h will be the change in the position of the center of mass of the sculpture. Okay, so delta y conc is the vertical displacement of its center of mass during the rotation. And recall, to find the center of mass, what you can do is use the summation mass times the distance from the particle to the position divided by the total mass. Okay, so for the hook, the axis of rotation, right, is where the center of the mass of the hook is. Okay, so we take the hook as one particle and the rod as one particle. So from the axis to the center of the mass of the hook, the distance is 0, so you have m times 0, plus this is the mass of the rod, m, then the distance from the axis to the center of the mass is r plus L over 2. Then you divide by the total mass, which is 2m. Therefore, the center of mass, right, is at r. That is before the rotation. Okay, after the rotation, the center of mass will be the same distance r from the axis of rotation, but now it's below because the whole thing is inverted. So the change in the displacement will be given by 2r. So we sub delta y const to be 2r, and from there we end up omega equals to 10.4 radian per second. There's a shortcut to this one. Part B, you can see that for the hook, right, when it's inverted, the center of mass is still passing through the axis of rotation. So you can see that the hook, actually the change in GPE is 0. So you can just take the change in GPE for the rod to be equals to the gain in rotational KE. You will also end up the same answer. Let's look at question 12. Okay, here you're given a large machine components that undergo prolonged long-speed rotation. First, examine for the possibility of failure in a spin test system. So in this system, a component is brought up to a high-speed well inside a cylindrical arrangement of lead bricks and containment liner, all within the cell that is closed by a lid clamped into place. So if the rotation causes the component to shatter, that means um, the, the rotational kinetic energy is so huge that the binding force of the lead, right, is not sufficient to hold the rigid body into one piece. Okay, so you're given some data. So in 1985, a solid steel, right, which is a disc. The mass is 272, the radius is 38 cm. Okay, so when the sample reached an angular speed of omega, there was a loud explosion. So what was the energy released in the explosion of the rotor? So the energy release is due to the rotational Ke. So firstly, to find the rotational Ke, which is half I omega squared, I need to know what is the rotational inertia, or moment inertia for the rotating disc. So recall the formula, I equals to half mr squared, and then you just substitute in. So the energy is of the order of 2.1 times 10 to the power 7 joules. Okay, with that, we are done with rotational inertia or moment inertia. Now we move on to the next section, which is dynamics of angular motion. So in dynamics, we talk about Newton's 3 laws. So similarly here, we also have Newton's 3 laws. The first law, Newton's first law, which is about moment inertia, right? The resistance to change its state of motion. If it's at rest, it remains at rest. If it's in linear motion, it will continue in that linear motion with a constant speed. Then the property, right, that resists the change in the motion is mass. So if you were to say in angular motion, then the angular inertia is equivalent to the mass, because the rotational inertia or the moment inertia resists the rotation. So rotational inertia is similar to mass in linear motion. Okay, so mass resists linear motion, rotational inertia resists rotational motion. Then for Newton's second law, we have in linear motion F equals to ma, but in angular motion, instead of F equals to ma, we will use torque, which is I alpha, where I is the rotational inertia, alpha is the angular velocity. Okay, so instead of force, we replace by torque. So the proof is here. Okay, you can take a look at it. I'm not going to go through it because it's quite easy to understand. Okay, what I'd like to explain is in this diagram, right? Notice this is the rotating mass. There will be a tangential force that give rise to the increasing linear speed, okay, the tangential speed. And then there is a centripetal force that gives rise to the centripetal acceleration because it's going around in a circle. Notice that this centripetal force, right, they call it the radiant force, is pointing out. Don't be alarmed by it. Okay, the centripetal force should be pointing towards the center of the circle, but this Fr is just a general notation of the force to show that it's a radiant force. So your centripetal force is actually in the direction opposite to your Fr. So you can say Fr, or you can say the centripetal force is minus Fr. The reason why most textbook, in fact all the textbook that I refer to, they have this radiant force pointing outwards is because they take the sign convention of the direction for the radius. Okay, radius is always from O to the particle. Okay, measured from respect to the axis of rotation. So the direction of radius is outward. So they just conveniently take the radiant force to be outwards. Okay, so the centripetal force is in the direction opposite to this radiant force. Okay, with that, we already looked at work example 10. Example 10, you are given a diagram shown below. This one have a uniform disc. This is like our pulley. Just that the mass now is not negligible. The mass is 2.5 kg. The radius of the disc is 20 cm, mounted on a horizontal axis. A block with mass m, okay, this is m, small m, 1.2 kg, hangs from a massless cord that is wrapped around the ring of the disc. Assume the cord does not slip. There is no friction at the axle. Okay, so to this question, you can draw free body diagram like what you have done it in the H2 physics. But the only thing different here now is there is a disc. So I should also draw a free body diagram for the disc. But when you draw free body diagram for the disc, you should be forming an equation for Newton's second law for rotation. That means you'll be looking at the torque, the moment inertia, and the angular velocity. But the block M, right, because it's going down in a linear motion, you can still use the F equals to ma, okay, the linear form of Newton's second law. Okay, so in this question, I repeat, to solve, we will have to consider the linear motion of the small m using F equals to ma, and then we need to consider the rotational motion here for the disc using torque equals to I alpha. Form two equation, and just like in H2 dynamics, we solve them simultaneously. Okay, in A part 1, you are asked to calculate the acceleration of the falling block. In part 2, radius of the disc is doubled. How will this affect the answer for part 1? Okay, let's take a look at how we find the acceleration of the falling block. We have the mass of the disc 2.5, radius of this 20 cm, and also given the mass of the block, m is 1.2 kg. So now I'm going to do a free body diagram. Because it involves rotation, so our sign convention is anti-clockwise is positive. That means if I were to draw a free body diagram, I will have tension here, right? If I extend the tension, can you see that it's going in the anti-clockwise direction? So this tension will be positive. Then the weight mg is going down. Okay, so if I turn towards the axle, it will be clockwise. So I'm taking T minus mg equals to ma. Instead of mg minus T equals to ma, because I take anti-clockwise to be positive. Okay, let T be the tension in the cord. Okay, next we need to form another equation for the disc. So for the disc, right, the rotational inertia is half mr squared. So the rotational form of Newton's second law, torque equals to I alpha. Given the question that the cord does not slip, that means you can take the linear acceleration of the block, okay, the small block m, to be the same as the linear acceleration tangential linear acceleration along the disk. Okay, that means the linear acceleration along this part is a constant. Okay, when we go to the disk, it is called a tangential acceleration. So the acceleration here will be constant. Because why? The disk does not slip. So for the top, right, it will be force times the perpendicular distance. The force will be the tension, which is going down. Because it's going down, if I turn towards the axle, this will be a clockwise direction. So the torque will be a negative torque, according to my sign convention. Okay, so torque is negative because this rotate clockwise from rest. So we take anti-clockwise to be positive. So the torque in this case will be minus RT I alpha. Alpha can be linked to the tangential acceleration by A in equation 1 by using A over R. So from here I simplify, I'll get the tension to be equal to minus half MA. Solving equation 1 and 2, I will have acceleration to be minus 4.80 meter per second squared. Why negative? Because if you take a look at the diagram, as well as my equation, I know that the block is coming down, right? So that's why I have MA, but coming down, if I turn towards the axle, that will be a clockwise direction. So to be consistent with my sign convention, I have a negative sign appearing for my acceleration. Since the effect of this A, which is the tangential acceleration, will turn the disk clockwise. Okay, B part 2, what is the effect on the acceleration if the radius is doubled? You can see from here that no effect because the acceleration is just dependent on the mass of the block as well as the mass of the disk. Okay, some of you asked whether in A part 1, is it okay that I actually ignore the sign convention that anti-clockwise positive, and then after I get the magnitude for acceleration, I deduce what is the direction. Can also. So if you were to do it that way, okay, probably for the block, right, you end up with mg minus tension equals to ma. So instead of equation 1, if I were to ignore the sign convention, that means I don't take anti-clockwise to be positive, okay, then I will have mg, small mg, minus tension T equals to ma. So this equation will be the other way around. And then for the second one, the torque, because I ignore the direction, I will just have RT, the magnitude, to be equal to I alpha. So I end up with magnitude, again, don't have the negative sign. Solving equation 1 and 2, I will end up with A being a positive value. And then you can just say acceleration is pointing downwards or in a clockwise direction with respect to the disk rotation. Now let's take a look at part B. You're asked to calculate the angular acceleration of the disk. So this is quite easy because we already have the tangential acceleration. So we call tangential acceleration is R alpha. So alpha will be A over R. A is minus 4.8 or just the magnitude 4.8. R is 0.2. So I'll end up with 24. Negative because it's going in a clockwise direction. So again here you can ignore the negative sign, you just go and calculate and then you deduce the direction. You can just say 24 radian per second square in a clockwise direction. Okay, let's take a look at C. Calculate the tension. So that's easy also. I can use equation 1 or equation 2 because I have the A, right? So you just substitute back. So the tension will be 6 Newton. Okay, some of you ask why I ignore the negative sign. Well, because respect to the disk, With respect to the disc, the tension, respect to the disc, the tension is downward, right? So it's actually clockwise. But respect to the mass, the tension is upward, so it's actually anti-clockwise. So calculate the tension in the cord. I'm using equation 2, okay? So I should add negative sign actually. But it doesn't matter because respect to the small m equal clockwise, respect to the big M, it is anti-clockwise. No. Respect to the small m, it is clockwise. No, sorry, repeat. Respect to the big M, the tension is clockwise. Respect to the small m, the tension is anti-clockwise. Okay, so I can just take either one. So whether positive or negative, not very important. Okay, again, if you find the sign confusing, okay, sometimes you get confused. 2, you can just ignore the sign. Okay, and this tension is 6 Newton. D, you're asked to describe the motion of the block if the mass is negligible. Motion of the block if the mass is negligible. Mass of the disk. Okay, so if the mass of the disk is negligible, that means your big M is almost 0. When you're asked to describe motion, usually we describe the S displacement, V velocity, and A acceleration. So you can look at the equations that we have in A. Okay, so the easiest equation to look at maybe is equation 2 because that is the one that have the big M. Straight away you can see the effect. Okay, I won't want to use equation 1 because the mass of the disk does not come into picture. Equation 2 is fine because when M is 0, then the tension will be 0. Or you can look at this equation also. If M equals to 0, then the small n cancel off, A will be equals to G. So it will be having free fall. Okay. So for equation 2, if the tension is 0, then you use from equation 1, the block will simply falls as the acceleration, as a free fall as the acceleration equals to G. Well, here I look at equation 2 and 1. Or you can just use this equation, the derived equation from 1 and 2, and then straight away you can deduce that A equals to G. Okay, with that we finish lecture 3. Next lecture, lecture 4, we'll look at work example 11, as well as the next few concepts. Okay, work and rolling motion.